So in this video we will study about the exception to the octet rule, and once again I would like to remind you about the octet rule, which we have studied in some early slides of this chapter. So Lewis electron dot symbol, or it is also called Lewis symbol. G. N. Lewis pioneered the use of the chemical symbol around the dot to symbolize the valence electron around an atom, and it utilizes the octet rule, which can be summarized as: so atom tend to gain, lose or shared electron until they are surrounded by 8 valence electron except hydrogen. So we have seen an example for methane gas, where the carbon have 4 valence electron and it is bonded with the 4 hydrogen. So in case of Lewis dot structure or Lewis single bond structure, so this carbon is sharing 4 electron with the hydrogen so that it can complete its octet, means 8 electrons. So 1 2 3 4 5 6 7 8. So usually every element tend to lose or gain or share electron so that they can completely surrounded by 8 electron, which is called octet rule. But in some cases the atoms do not follow the octet rule. And what are those conditions? Number 1, Lewis dot structure that have an odd number of total valence electron. If valence electron number is an odd, 5 7 9 11 13, like that. So Lewis dot structure that have less than octet around the central atom, so they may have less than 8 electron. So valence electron will be less than 8 electron, and here the valence electron will be like 3 5 7 9 11 13. So these are the octet odd number. And valence dot structure that have more than an octet around the central atom, so central atom have more than 8 electron, so electron are more than 8. So these elements or these atoms do not obey the octet rule, and let's see some examples so that we can understand better. And number 1 exception is with odd number of electrons. So Lewis dot structure that have an odd number of total valence electron. For an example, NO, nitrogen and oxygen, when they form a covalent bond. So when we will count their total electrons, so nitrogen have 5 valence electron and oxygen have 6 valence electrons, so total 11 electrons are there, and they do not follow the octet rule. So we can write like this one, that nitrogen is forming double bond with the oxygen, and so we can write their structure like this one. So nitrogen have 5 electrons, so 1 2 3 4 5 and 6 7. So total for this nitrogen is 7 electron. For this oxygen, 1 2 3 4 5 6 7 8. For this oxygen, total 7 electron. Or another way, 1 2 3 4 5 6 7 8. So we can complete the octet for the nitrogen, but we are not able to complete the octet for this oxygen, 1 2 3 4 5 6 7. So nitrogen oxide or NO is one example where the dot number of electrons where the it has odd number of total valence electron. So this is exception of the octet rule, which is the first example. And another example we will study, that where they have fewer than 8 electron. So Lewis dot structure that have less than octet around the central atom. So for an example, BF3, boron trifluoride, So boron have total 3 electron and fluorine have 7 electron. So when we will count together, so 7 times 3 21 and 3 24, so 24 electrons are there. So when we will write the structure of this one, you can see boron have 3 electrons, so this is shown by the red dots, boron electron, and remaining the electrons are shown for the fluorine. So fluorine has 7 electrons, 1 2 3 4 5 6 7, and 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. So you can see how many electrons has been used completely. So 1 2 3 4, and if so each fluorine will have 8 electron, one this one, this one, like this one. But the boron, when we'll count the boron has only 6 electron, so it is less than 8 electron. Let me see, let me show you. So it's supposed to be, basically it's supposed to be one more electron, but they are not here, right? So this does not follow the octet rule. So once again, elements in the second period before carbon can make the stable compound with fewer than 8 electrons. So second period, and considering, so giving boron a filled octet, place a negative charge on the boron and a positive charge on the fluorine. It would not be an accurate picture of the distribution of electrons in BF3. So in BF3, either we can write, if we want to complete the octet of the boron, it would be like a 1 2 3, we can make a 1 double bond between to each other, and but we have to give a negative charge on this one. So 1 2 3 4 5 6 7 8, and this fluorine has 1 2 3 4 5 6 7 8, and each fluorine is also. So giving the boron a filled octet, place a negative charge on the boron. So you can see, if we are going to make a negative electron, if we are giving to one trying to complete the octet of the boron, it by making a double bond, it will have a negative charge, which is less important, or less not in which is not prominent, and a positive charge on the fluorine. But this would not be accurate picture of the distribution of electrons in the BF3, but the dominant structure of this one. So in second period, and the element can make a covalent bond with the less than 8 electrons. One more time, just to look this one. So if filling the octet of the central atom results in a negative formal charge on the central atom and a positive formal charge on the more electronegative atom, outer atom does not fill the octet the central atom. So we can also decide using the formal charge rule. We can find out, we can write the formal charge for each fluorine and boron with, for these electrons, for these for these structures, and for this structure also. And based on the formal charge, it will result basically a negative formal charge on the central atom. A negative formal charge will come for this boron in each cases, and a positive charge will come on the each fluorine for the fluorine which is have double bond in each structure. So that is why this these structures are not correct compared to this one. So this boron can remain stable without octet. So let's see some other example where exception number 3, where it has more than 8 electrons. So Lewis dot structure, that have more than an octet around the central atom is these are example here: PCl5, SF6 and SF4. so common for third period elements and the higher. So so just one more time, this exception number 2, which is common for the second period, for the boron which is in the second period. So if we will write the periodic table, so this is the first period, number 1, and then this is the second period, number 2, number 1, number 2, and then so the elements which are in the second period from here in the periodic table, they have usually less than 8 electron, and so they are exception of the second exception of the octet rule. And in case of exception for the 3, where they have more than 8 electron, so what type of those electron elements or atom, they do not follow they come in this exception. So this is a period number 1, period number 2 and period number 3. So elements which are in these period starting from the number 3, common for the third period and higher. So from third period to higher, they usually do not, they are kind of exception because they can have more than 8 electron in there. So let's see some example, we can understand better. So more than 8 electron, when an electron is in the period number 3 through 6, so starting from 3 to 6, it can use d orbital to make more than 4 bonds and be hypervalent. So why it is the exception? Because they have d orbitals free, so they have many extra orbitals free, and they can fill d orbital by other elements. So for an example, PF5, phosphorus pentafluoride, and phosphate below. So these are the two examples. This is the phosphate ion, PO4 minus minus minus, and PF5. So phosphorus have you can see here how many electrons is sharing: 1 2 3 4 5 6 7 8 9 10 10 electrons. In case of phosphorus here, 1 2 3 4 5 6 7 8. So these are the some examples, the elements which are in the third period and higher, they do not follow the octet rule, or they are in the more than 8 electrons. Another example is sulfur tetrafluoride. So sulfur have the 6 valence electron and fluorine have 7, so total 34. And when we will write electronic configuration, so we can share the 4 electron between each fluorine. So like this one, S, so fluorine, fluorine, fluorine and fluorine. So each fluorine have single bond, and you can see this basically it is satisfied. Each fluorine have its octet is complete. It has 7 electron and 1 electron from sulfur, so 8 electron is complete. But if we will count the sulfur atom, so have 1 2 3 4 5 6 7 8, but sulfur have total 6 electron. So we have to leave one pair of lone pair electron here. So when we will count total, so it will be 1 2 3 4 5 6 7 8 9 10. So 1 2 3 4 5 6 7 8 9 10 10 electrons. So sulfur hexafluoride tetrafluoride is also another example for the exception of the octet rule, which have higher electrons. So these were the examples about the octet rule. And here is one question, that which one of the following molecule follow the octet rule. So you can draw the Lewis structure for BF3. Which of the following molecule follow the octet rule? So here they are not asking the exception, which basically they are asking which really follow the octet rule. So you can try to draw the structure and find out which is exception number 1, which come exception number 2, and which come exception number 3, or they follow the octet rule. So this will be your kind of homework. Try this one.